What we're going to do now is relate our knowledge of factoring and integrate it with our polynomial functions and how it can be used to get the x-intercepts. So the first example that we've already looked at was the y equals x cubed minus 4x. Now, if we think back to our factoring, we always want to look for a common factor first. And I noticed that both of these have an x in common to them. So I'm going to common factor x out of both terms. So x cubed divided by x would be an x squared, and then minus 4x divided by x would be minus 4. Now I'm noticing in that bracket, x squared minus 4 is a difference of squares. So that could factor to x take away 2 and x plus 2. Now, based on that, and based on what we've just talked about in the previous video, I know that I could take each factor and set it equal to 0, and then solve the mini equation. Well, the first one's really easy, x equals 0. So that tells me we have an x-intercept at 0, 0. So hopefully that makes sense there. And then we have x minus 2 equals 0. If I add 2 to both sides, that gives me x equals 2. And then that gives us an x-intercept at 2, 0. And then this last one, x plus 2 equals 0. Goodness, x plus 2 equals 0. And then we get, subtract 2 from both sides, we get x equals negative 2. So that gives us an x-intercept of negative 2, 0. All right, if we look at the next one, let's see what else we can do with that one. If I look for a common factor first, like I always should, I'm noticing that I can divide everything by 2, and they all have a factor of x. And in fact, I'm going to take a negative 2x out because my leading coefficient is a negative. That gives me an x cubed divided by x would be x squared. I would have a plus because a negative divided by a negative is positive, and I would need just a 1x or just x. And then we would have to have a minus and a 6 as a last term. Now in that bracket, it is a simple trinomial. I'm looking for two numbers that are going to add to 1 and multiply to negative 6, and I believe positive 3 and negative 2 will do that. And then because it's a simple trinomial, I can use those numbers directly to be put in the brackets as factors. So we're going to have an x plus 3 and an x minus 2. All right, setting each one of those little mini equations, or mini factors, equal to 0, we're going to get x equals 0 out of the first one. It would be minus 2x equals 0, but if we divide negative 2 from both sides, we're going to just get x equals 0 out of that. And I've done this enough times that I know that, but you know, that's what happens with that negative 2 out front. So that gives us an x-intercept at 0, 0. The next one, we get x plus 3 equals 0. Oh goodness, I'm having trouble here. Let me try that again. X plus 3, I'm still having trouble, equals 0. And then subtract 3 from both sides, we're going to get x equals negative 3. So negative 3, 0 is an x-intercept. And then x minus 2 equals 0. Add 2 to both sides, and I get x equals 2. So that gives us an x-intercept at 2, 0. So compare the factored form of the polynomials above to the x-intercepts. What do we notice? We notice that we can get the x-intercepts from that factored form. Okay, so we notice that the factors are related to the x-intercepts. So if we set each factor equal to 0, solve the mini equation, we get what the x-intercept is going to be. All right, example 3, graph each function using technology and complete the table. What happens at the x-intercept when a factor has an exponent other than 1? So this first function, we should be able to predict what the degree is going to be, what the sign of the leading coefficient should be, the end behaviors, and the zeros. But what I'm interested in by using our graphing technology is what is happening at the zeros when it has an exponent that's greater than 1. So for example, in the second equation here, we have an exponent of 2 on the factor of x minus 2. What is happening at that x-intercept of 2? And on the third one, we have an exponent of 3 on the x minus 2 factor. So what's happening at that 0 of x equals 2? So that's what our goal is with this. So put the video on pause, work through this whole thing. If you're not sure how to get the degree from the factored form, you don't actually have to do a full-on expand and simplify. I know that if I multiply x with x, I get an x squared, and then an x squared multiplied another factor of x gives me x cubed, multiplied by another factor of x gives me an x to the 4. So my degree of this polynomial is 4. And since we have a positive x times a positive x times a positive x times a positive x, but it's all multiplied by a negative 1, the sign of that x to the 4 will be a negative sign. Okay, so degree 4, leading coefficient, we should have something that looks like this in terms of end behaviors. So as x approaches negative infinity, y is approaching negative infinity. And as x approaches positive infinity, y approaches negative infinity. And our zeros here should be at negative 1, comma 0. Oh, I'm not doing very well with this writing on the iPad. This should be a 2, comma 0. We should also have a factor of negative 3, comma 0. And a factor of 4, comma 0. Okay, a factor, I should say x-intercept. These are coming from the factors, but they are x-intercepts themselves. All right, so all of those should produce a nice little quartic function, degree 4 function. Try the next one, see what's happening at the exponent of 2 and the exponent of 3, at the 0 when x equals 2 and when x equals 2 for the third one. Okay, if you've put the second equation into your Desmos or graphing technology, this overall should be a degree 4 because we've got an x squared happening here when we square that binomial. An x squared times another x would be x cubed times another x would be x to the 4, and overall our sign of the leading coefficient will be negative, so that means y approaches negative infinity both when x approaches positive and negative infinity. Now this one only has 3 x-intercepts. We have one at 2, at negative 3, and one at 4. And while these two, the negative 3 and the 4, they just cut straight through the x-axis, the graph kind of bounces off the x-axis at this one. So it looks like that order of 2, that degree of 2 on the factor of x minus 2 is creating something different at that x-intercept. Likewise, when you put an order of 3 or an exponent of 3 on that factor of x minus 2 in the third one, you're going to notice it doesn't bounce off of the x-axis, and it doesn't directly cut through it either. It does something funky there. So put that one into your Desmos, see what happens. This one's also degree 4 when you expand and simplify. It is a negative lead coefficient. It is still y approaches negative infinity both as x approaches positive and negative infinity. This one only has 2 x-intercepts happening, one at 2, 0, and the other one at negative 3, 0. Now if you put that into Desmos, you're going to notice that it does pass through the x-axis, but instead of just cutting through like these other ones did, cutting through your x-axis, and as opposed to bouncing off the x-axis, this one does something funky. It gives you a little twist in the graph at that value of positive 2. And I did that graph backwards, I just realized that. If I actually did this on a Cartesian plane, bloop, bloop, we have our negative 3 happening here, we have our 2 happening here, and behaviors. This one's going to cut through. It's going to do something like this, where it has a little bit of a twist. We do the twist at that x-intercept. So it has that S shape like a cubic does. All right, finish up with the last 2 examples there, and then make a conclusion based on your findings. Okay, I have my results here. The fourth function has only one x-intercept here, and it has the graph, when you graph it, has a bounce happening off of there, off of that value of x equals 2. So we have our graph looking something like that. So again, an even order on the factor will make a bounce off the x-axis. Similarly here, you should have found that your graph bounced off of those zeros at both -3 and +2. So your graph comes up like this, bounces off, and does something like that. Okay, so the effect of the graph on the graph of a polynomial function when a factor is repeated, an even number of times means that the graph will bounce off the x-axis at that point, at that 0. If it's an odd number of times, if it's just 1, it cuts straight through, but if it's an order of 3, then it's going to do the twist at that spot, or a zigzag, or whatever you want to call it that tickles your fancy. All right, so I'm just going to summarize that here. Okay, so an even number of times means the graph will bounce off the x-axis at that intercept, and if the exponent, for the odd number of times, if the exponent's a 1, the graph just cuts straight through the x-axis. If the exponent, which is also known as the order, is a 3, then the graph twists at that x-intercept. So for example, let me just grab my proper tool here. If I had an order of 3, my graph will come up and twist at that spot, at that x-intercept. Okay, so this would be an order 1, or exponent of 1. This could be an exponent of 3. So let's put order 3. And if you had a 5 as your order, it just means that that twist will be more dramatic. The higher the exponent is, the more dramatic the twist becomes. And likewise with the even number of times, a order of 4 will flatten it out more at that x-intercept than an order of 2 will. That bounce will be more flattened. Think of a ball that doesn't have a lot of air in it. It kind of squashes down towards that x-axis. All right, hope that makes sense for you. Now complete the rest of the handouts.